Hi, and welcome to Core Concept 1, second part. So I might have a third part, I don't know yet. Where are we? We're at I would say, the best equation in mechanics. I really, really love this. Distance traveled, is initial velocity times time, plus the sum of, right? 1/2 acceleration times the square of time that has elapsed. All right, what are we going to do with this? We need to build this out a little bit, and I thought, best way, easiest illustration, and something that makes a lot of sense, also allows us to introduce a couple of concepts here, would be to look at a vertical drop. All right, so we'll start here. That is a building. Put some whatever windows and doors. Tall building. Okay, what happens here? Let's take a look at this. Let's say we drop something off a building. Don't do it. That experiment has been done. And let's say that object has mass m, and we drop this object coming straight down here. We could measure the height of the building, right? We could determine S. If you had stopwatches, you would relatively, not so accurately measure time that passes. You know initial velocity here, well, that is 0. That's why this special case is interesting, because it allows us to play with this equation a little bit. What else do we know? We know mass, m, let's say, t, acceleration. Now, here's what I wanted to introduce, right? So there is a, so you could say, hey, a speed cam right there might be able to tell me what final velocity is, and I could calculate acceleration based on that. But it would be very difficult, because that exact point of impact, very, very difficult. But with technology, anything is possible. But let's just say we have initial velocity, we have some final velocity, right? And we have acceleration. Now this is a special case. Obviously that's why I chose this, because I wanted to illustrate this concept of acceleration due to gravity. You just drop something, it's free fall. Acceleration due to gravity, in effect, because of the Earth, and if you were on the Earth, you would write A here in its special case. A is equal to, and I'm going to use this attempt at a cursive artistic G for acceleration due to gravity, and we know it is 9.8 meters per second square. That is an important concept. If you know this, now you wouldn't need a speed cam, or maybe a stopwatch. If you dropped something off and you heard the loud thud as it landed, you could measure time. You would know the height of the building, just measuring tape, right? You could calculate a more accurate value of V. Or if you did have that really sophisticated speed cam and you snapped that picture, you knew how much time had passed because you had a camera there that spotted exactly the instant when you let go. You had another camera, they captured time, you could calculate distance. All of that using this formula. I'm not going to illustrate that, but it should be fairly self-evident. If you need help, leave me a comment and I'll do that. But let's build on this, okay? So what's going on? Well, there is no mass. There is no mass anywhere, which means time, and if you look at this, let's just play with this a little bit, because we love math. In this special case, u is 0, that equation simply becomes S is equal to 1/2 g times t squared. T, therefore, you guessed it, is the square root of 2 times s divided by g. Plus or minus? No. Time in our universe is positive. Tachyonic universes have negative time when mapped to us, but lesson for another day, another time, another universe. 2 times s by g. So it does not have a correlation with the mass. For a fixed height, if you dropped an object, assuming no other variable, right? No surface air resistance or anything like that, right? We'll get to all of those in later parts of this course, maybe in the advanced section where we do terminal velocity and things like that. But left on its own accord, all objects would take the same time to reach the earth if dropped from a particular height. People did try to drop feathers and bricks and rocks and eventually had to reconcile this because they realized that it was air resistance that was causing some objects to be slower. But if you had exactly the same profile, you would technically be, you'd have the same time. There's no function of mass. Now let's take this one step. Actually, there are two things I wanna cover here. Right? First is you've got mass, the amount of stuff, but you also know that on Earth there is a constant acceleration due to gravity. So you fall, anything falls, and it's that fall, or it's that fall means there's a force, right? You've got acceleration due to gravity, you've got mass. Here's what I want to introduce. I want to go back to force is equal to mass times acceleration, and then say if you had a mass, it's always subject to g. Mass times acceleration is a force which we would know as, you guessed it, weight. Very important. Mass, the amount of stuff, amount of material, amount of matter. G, what the earth does to that matter. Result is weight. People use this as kilograms, mass is kilograms. They confuse. In reality, you could argue that weight should be in newtons. Oh, that'd be nice. How much do you weigh? I'm 88 newtons. Well, I don't know. It'll be a tough one. But if you look at something like a body mass index, so they get it right there because it's really a ratio and the factor of G is being cancelled out. So you could then argue that that's really, you're not taking weight, right? Because you're really looking at just mass. How much of something is there? So it's the expression is more accurate there, but for some reason, when it comes to us, we would just weigh it. It's the weight, and then we just use kgs or pounds or same definitions of mass. But important to remember, weight, right? And it's a type of force because it is really mass times acceleration. What happens to this mass when the Earth exerts acceleration due to gravity, which is g, is what you get as weight. All right, that's one part, right? And now I introduce m being impacted by g. I want to take this, and we also know that there is no relationship between mass and the time something takes to fall, which means velocity is also unrelated to mass. At any point here, this mass is subject to g, right? Anywhere you were, there's always G is acting fairly constant within reasonable heights. Obviously, if you go a light year away from the Earth, there's no effective G, but within reasonable. So what is going on? Are we going to say that the force on this force, the force of an object anywhere is that? In which case, well, if I fell off or if I jumped off here, I might land and still be okay. But if I did attempt something from here, I know probably not, there'd probably not even be a piece of me. So very intuitively, we know that the higher you went and higher you dropped, you'd kind of be met with a much greater impact. Yet, force at any time on that object is, due to gravity, is here. So what's going on here? So somewhere we need to reconcile what's going on, and that is really where I again introduced everybody to conservation of momentum in line with Newton's third law. So if you already know this, and here's your first assignment, you can pause this video and attempt to demonstrate what is going on here mathematically if an object is going to fall. Let me try this here. Let me do this and set up some math here. So I have a very hot surface, right? And let's say I go up, call it 15 centimeters, right? And I drop this. Okay, that looks okay. Now I know this board is 120 centimeters. So if I go up here, and let's try this. Ooh, 3 pieces. Clearly, something happened. There was a function of mass, it was just not m times g, that stayed the same. What happened, right? Why did this chalk break at a greater height, right? And what I'd like to do is pause it, try to work it out. If not, work with me on this. I had the first case where the chalk was intact, and I had the second case where the chalk was broken. You would argue the weight didn't change, it was the same chalk. Right? In either case, let's just say its mass (10 grams). 1,000 grams is a kilogram, 10 grams is 0.01 kilograms. That didn't change in both cases, right? Chalk broken, chalk intact, that didn't change. S did change. S here was about 15 centimeters, so that would be, what is that, 0.15 meters. S in this case was, say, 1.2 meters, about there. That we know. Initial velocity didn't change, they were both at rest. U was equal to 0 meters per second. So we're approaching that special case. We know acceleration, I didn't really throw it. A was g, which is 9.8 meters second square. That hadn't changed. Well, clearly, time would be different, the amount of time, because s is here, we know that. But still, this chalk felt like it met with a much greater impact, got hit by something harder, and it broke. What happened? What happened is when we look really, really closely here, it came down and just crashed onto this. Now this, I was holding that tablet, it's connected to me, I'm grounded, so effectively very, very massive for all practical purposes. But it came in here, and from a smaller height, it clearly didn't get that much of an impact. Newton's third law said if something came in this way and caused impact, there'd be an equal and opposite reaction on it this way. So let's say the Earth gave it a knock back. That knock was not serious or not damage causing here, but clearly broke it into 3 there. So much heavier knock, much stronger. Why? If mass times acceleration is constant, it must be just constant force. What happened here, that is where we will go to momentum, right? What happened as you went down, you kept increasing your velocity because of that constant acceleration. So what might have been the final velocity here? That is the question that we will first attempt to answer. So let's do some math here, just move it around, plug it into this equation or one of its derivatives. You should get, if I did 2s 4.9, that becomes, so if I did 0.15, in this case I would say my time is, call it 0.175-ish, 0.39.8 should be, and then the square root, so I think it's right. And a factor of that, 1.2, that's 2.4. My time is here. Yeah, about there. You can do the math. And if I did that, velocity, initial velocity is 0, so final velocity v, about 10. This is seconds. Never miss your units, never miss your units. Bad me. Sometimes simpler math is. I think I'm there. I just approximate this to be 10 and then take that 5 out, so approximately I think this should be correct. You could do the math, but I think that we can illustrate the principle a lot better. So you came down here with a velocity v, in the moment of impact, that velocity became 0. That is a massive drop in velocity. What happened to the chalk when it was intact is it was subject to, let's do momentum now, right? If its mass was 0.01, it was subject to a change in momentum. I'm just going to go here and just do change in momentum. Mass didn't change really, so I'm just going to keep mass there and say its velocity went from 1.7 meters per second to, well, actually, final velocity was 0. In a very, very tiny instant of time. That doesn't change, right? The instant of time doesn't change, and if I did that here, I would do mass times 0 minus 4.9 in that very tiny instant of time. Now that instant of time is very, that's change of momentum, and that is force. That instant of time is really, really small, so even if this mass velocity difference, this momentum difference was small, that instant of time is so tiny that it could generate a much large, or rather quite a large force. Obviously, the more massive the object, obviously the force is much larger. So if you dropped a really heavy object, you'd break the floor, or you'd create a crater. If it was light, like this one, the object obviously took all of that burden, right? And why do we do this? Because we know from the basic section we saw, the last part of basics, we know that when you came in and hit the Earth's way too massive, it really didn't move. There wasn't any effective transfer of momentum to the Earth. So everything that this force that was created by your velocity suddenly dropping, that the factor of acceleration that came in the change of momentum, everything that happened here, F, got returned by an equal and opposite force, negative F. So here the force was not as massive. Here it's almost 3 times as massive. Assuming M and T stay the same, your force function here, if M and T were all, say, unit values, let's just say negative 1.7, negative is just is a direction, gets hit back by the negative of negative 1.7 newtons, here you would be getting knocked back by 4.9 newtons, so 3 times as much force, because I raised it up a little higher, right? And that hopefully illustrates to you what happened. The shock broke, and that was Newton's third law, where you got hit. Why did Newton's third law come in? It always does. But in this particular case, it came in with full effect, because the object you were colliding with did not have any momentum that it took, because its mass didn't change, its velocity didn't change, it was the Earth. Therefore, all of that momentum, because of the conservation of momentum, gets returned back, right? And that return, obviously this is not elastic, it didn't bounce back, it took that impact. That return is really the force, that reactive force that came in, took it, broke the shock when it was dropped from a taller position or a higher position, right? And that is the explanation to it. If you figured this out, great. If you hadn't, hopefully this serves as an exercise for you to remember how, even though that looks like it's constant, what you really need to evaluate is what happens at the point of impact, and then apply the principle of conservation of momentum in Newton's third law. And that is how you'll encounter a lot of problems as well. They may not be necessarily vertical drop, but they'll be, even on a horizontal axis, you might have problems where objects collide and things like that. Okay, hopefully this clarifies, but also creates a segue to the next thing I would probably cover, which is, you saw the negative that I put in here. You've got a negative value here. Force really does not become negative. You also saw that in the basics when we get a velocity equation. It was negative. It was really that roll of tape coming back at me. So it was really that direction. And this is probably the right time to start talking about direction. And when we bring direction, we're going to talk about vectors, scalars and vectors. I think that will be the next section. We'll see you in that one. Until then, digest these. Good luck.